Cool. Welcome to our last Thursday seminar of this term on climate prediction in the 2020s. So as the world meets in Paris, the issue of predicting the climate in order to provide scientific input into climate policy is hugely topical, and we have a superb guide to the subject today. Professor Tim Palmer is the Royal Society Research Professor in Climate Physics here at Oxford and is a professorial fellow at Jesus. Here at the Oxford Martin School, he is co-director of the programme on modelling and predicting climate, and he's also a PI on the Oxford Martin programme on resource stewardship. He's been involved in all 5 IPCC assessment reports, was co-chair of the International Scientific Steering Group of the World Climate Research Programme project on climate variability and predictability, served on many government committees looking at issues from climate adaptation to the role of science in helping mitigate the humanitarian impact of natural disasters. He also serves on the Met Office's Scientific Advisory Committee and was honoured this year in the New Year's Honours List with the CBE for services to science. So a great guide to this important topic. Tim will be talking to us, and there'll be plenty of time for questions and answers afterwards as well. So welcome, Tim Palmer.
Okay, thanks, Julian. Well, it's a pleasure to be here, and thank you to all of you for coming out on a bit of a gloomy evening, but I suppose it's at least dry so far. Just to be absolutely clear, I'm not going to talk about what the climate will be like in the 2020s, but rather what our capability of predicting climate well, at least what I would like it to be like in the 2020s. Whether we get there or not remains to be seen. Let me sort of outline the talk. I'm going to sort of start off by trying to convince you that, maybe many of you don't need convincing, but why it's so important to aspire to be able to predict reliably, and by reliably I mean in the sense that society can make decisions based on the information, why it's important to predict climate on different timescales from seasons, years, decades and centuries ahead. And in particular, what are the current sort of shortcomings in our capabilities? So what do we need to do to improve things, and how can that be achieved? And I want to discuss some specific issues to do with the organisation, a particular issue of supercomputing, which is of concern to me, and the general issue of human resources. So I want to start with why we need to predict climate. I'm actually going to lump weather a little bit into this, because the boundary between weather and climate is not totally clear-cut. So there's a kind of a bit of a gradual smeared out distinction between what we call weather and climate prediction. So I'm going to focus on each of these topics for a few minutes each, but the main move towards more important applications for society. So just to start, it is important to make the point that the predictions are now, universally around the world at different operational centres, are made with computer models which attempt to solve the basic equations of physics. So these could be described in part by Newton's laws of motion, in part by the laws of quantum mechanics, which govern how photons from the sun are absorbed in the atmosphere or scattered back to space, and how indeed photons are re-emitted at lower frequencies and transmit back to space. And then finally, through the laws of thermodynamics, this is Rudolf Clausius, who is the father of the concept of entropy and the second law of thermodynamics. So the combination of Newtonian mechanics, a bit of quantum mechanics, and certainly a lot of thermodynamics is basically the underpinning for all of the attempts to make predictions. So we very much moved away from the sort of rules of thumb or folklore or whatever it is towards hard science. And that's sort of the basis of my talk, the application of hard science. You might imagine that perhaps, quantum mechanics being notoriously unpredictable and uncertain, that might be the biggest source of uncertainty in our ability to predict climate. But actually it's the least uncertain And in fact, it's the ability to solve Newton's second law of motion, which actually turns out to be the most challenging of all these things. And the reason is that Newton's laws of motion apply to essentially a continuum fluid, which is the atmosphere and the oceans, which means it applies on all sorts of different scales, from, say, the very largest jet stream scales, really right down to the scales of my breath coming out of my mouth, centimetre or even millimetre scales. And these scales are in principle coupled together through this equation, which is really just an expression of Newton's second law of motion, force equals mass times acceleration, for a fluid. It's just an expression of that F equals ma in terms of what's called a partial differential equation. So I'm not going to attempt to say anything too much more about this, except first of all to say that it is a wonderful equation mathematically, that it can kind of compress all that information about many sort of zillions of scales of motion into one piece of mathematics with just some 20-odd symbols. And in some sense, one can equate it to a work of art. The work of art I'm going to use is a Russian doll. And the reason for this is that the Russian dolls unpack into smaller Russian dolls, and this particular Russian doll is a very special one because it unpacks into millions and, in fact, billions of Russian dolls. And in a sense, that describes the complexity of what's called the Navier-Stokes equations, the F equals ma for a fluid, because if you want to actually solve it, you also got to unpack it into these potentially billions of individual equations describing the individual scales, from the very largest jet stream scales or Gulf Stream scales down to individual small eddies. And we don't have big enough computers to do that, and so we have to essentially start chopping out scales when we solve these equations, so we get rid of a lot of scales. And typically climate models that predict out for 100 years might go down to about 100 kilometre resolution or so, a few hundred kilometres. Weather forecast models that are only predicting out for a few days every time they're run can make do with much higher, or the computer power allows them to have higher resolution. So typically weather forecast models might have truncation scales around a few tens of kilometres. So whether it's 100 or 10, that means that all cloud systems, if you think about individual clouds in the sky, whether it's a little puffy cumulus cloud or a big thunderstorm type cloud, these are all basically subgrid scale. And therefore, but nevertheless, clouds are crucially important. They block radiation from the sun, or indeed from the Earth, re-emitting it in the infrared back to space. And they're important sources of energy when water vapor condenses into liquid water. The latent heat release in thunderstorm clouds can be enormously big in driving circulations. So we can't resolve them in global climate models, so they have to be represented in a rather simpler way, and that's this sort of slightly rusty tin can type of shape, which is just indicative of the fact that the elegant beauty of the Russian dolls is kind of is somewhat destroyed at the truncation level, and in a way it's the simplified approximations that have to be put into the models to represent unresolved but nevertheless important processes that are one of the fundamental sources of uncertainty, particularly on climate, for climate predictions. So I mentioned about weather and climate, so let me just sort of show you this schematic, which is it's kind of a function of timescale, showing different types of prediction horizons. So we might be sort of making a forecast for next week, or maybe next season, or next decade, next century, next millennium. Broadly speaking, one could divide this into two classes. When you're making a prediction for next week, you're essentially taking the initial condition, the weather today around the world as an initial state, and using those Navier-Stokes and other equations to sort of propagate forward in time that initial state to some future state, 7 days ahead or whatever. So that's mathematically an initial value problem, and it means you have to know your initial conditions as well as possible to make good predictions a week or so ahead. When we come out to these long time scales of a century or a millennium, the nature of the prediction problem is different. It's not so much an initial value problem as trying to estimate how the statistics of weather are going to change as, for example, we double the amount of carbon dioxide in the atmosphere from pre-industrial values. Or on these longer timescales, maybe we want to estimate how changes in the orbital characteristics of the Earth around the Sun affect, again, the statistics of weather. So there's this kind of sort of duality here between the short timescales being initial value problems and the longer timescales essentially being what you call forced problems, or sometimes called boundary problems, but I think forced problem is a better one, where you're not trying to make a specific sort of prediction in time about a specific sort of weather pattern, but just generally trying to estimate how changes in the statistics of weather are affected by, as I say, either, say, increasing CO2 or maybe some changing orbital characteristic. On the seasonal and decadal timescale, the initial value problem is not just one for the atmosphere only. On those timescales, it's crucially important to have good initial conditions for the oceans, because they play a major role, as we'll see, in making seasonal or decadal predictions. So, for example, the El Niño phenomenon in the Pacific Ocean is something which I'll talk about in a few minutes, but making an El Niño prediction requires very good observations in the tropical Pacific Ocean. On decadal timescales, people think about what's called the thermohaline circulation, the big overturning circulation in the Atlantic Ocean. And again, trying to predict how that's going to vary over the next few decades, again, requires good initial values of that overturning circulation at initial time. And for that, you need in situ oceanographic observations. The distinction between a forced problem and an initial value problem is not actually as clear-cut as I'm showing here, because on a decadal timescale, you might be interested in knowing, as I say, how the thermohaline circulation is going to vary given its value today. But you additionally have the effects of increasing levels of CO2 over the decade. So actually on this sort of, between the red and the blue, it's actually a sort of slightly blurred, should really be a fuzzy line, not a sharp line. Historically, we've tended to call weather forecasts just forecasts or predictions out to, say, a week or 10 days or maybe a month, I don't know, ahead. And once we get into the seasonal and longer timescales, that tends to be called climate prediction. I think the reason for that is that when you're making predictions on seasonal and longer timescales, you need a model that is essentially a full-blown climate model. In other words, it has an atmosphere, it has an ocean, global ocean, it maybe has some representation of sea ice, and it has, you know, good representations of land processes. So, whereas for weather forecasting on very short timescales, you can just pretty much get away with an atmosphere-only model and treat the sea surface temperatures as a sort of fixed lower boundary condition. So the terminology really is that we're talking about climate prediction from maybe a season out. So let me just run through these timescales really just to make the point about why it is important to have predictions. So I'm going to start by just drawing your attention to a very recent report by the UN Disaster Risk Reduction Agency, UNISDR, who make the point that, according to their analysis, 90% of disasters are weather-related, natural disasters. So this can be flooding, could be heat waves, drought, and windstorms, and so on. Perhaps the one that's sort of most famous for causing devastation is the tropical cyclone. This is a picture of Haiyan, which I think broke all records for a land falling, a tropical cyclone that hit land in the Philippines a couple of years ago or so. And this is the sort of weather phenomenon that's projected to increase in likelihood with climate change. Now, I've got here from a sort of Wikipedia page some of the most deadly of the tropical cyclones. over the years. And for example, the top one in 1970 was estimated to have killed somewhere between 250,000 and 500,000 people. And if you go back into that era, one can regularly find instances of these tropical cyclones that killed either directly through the winds or often through the storm surges that these cyclones create, killed upwards of 100,000 people. But if you look at this table, with one exception, which is Cyclone Nargis in 2008, none of these tropical cyclones killed anything like that number of people. And in fact, if you look at today's tropical cyclones, it's rare to find more than a few tens maybe of people being killed. And that's certainly because our ability to predict these cyclones has improved enormously. A second point is that information through mobile telephones and stuff getting out to people in the field is much better these days, so the information is also getting out there. But this, I think, is one of the real successes of numerical weather prediction, the ability to save lives in predicting days ahead of time the landfall and the intensity of tropical cyclones. Cyclone Nargis actually was the topic of a commentary by a colleague of mine, Peter Webster, at Georgia Tech in Atlanta. And he made the point that the reason why Nargis killed so many people was that the government authorities didn't alert the population of Myanmar to this oncoming storm, which was very well predicted by international agencies. So this was not a failure of numerical weather prediction, but a failure of communication. I think he's called it deadly daffodil because Nargis is Urdu for a daffodil. Now, I just thought I would tell you something which you're probably not aware of, and it's particularly pertinent these days as we start to kind of question the whole concept of Europe and our potential membership of Europe, and the European dream of a collaborative partnership with our local countries. And that is that we are the best in the world at predicting weather. So here's just a few slides or web stories from various sources. National Geographic. This was predicting a snowstorm somewhere in the US. This was predicting a hurricane in the Atlantic. Why has the US model fallen behind the European model? This is why European forecasters saw Sandy, the famous hurricane that hit New York, well before the Americans and others, Hurricane Schwartz, and Scientific American saying why are Europeans better than Americans at forecasting storms. Now, when they talk about Europeans, what they're actually referring to is a centre only about 25 miles from here in Reading. Probably not a place you've ever heard of. It's kind of set down a road just south of the university campus, sort of on your way to the M4, a very unlikely place for a world-leading meteorological centre, you might think. But nevertheless, there it is. It's called the European Centre for Medium-Range Weather Forecasts, and it's just actually had its 40th anniversary, and it's set up as an example of European collaboration. It's funded by about 30 member states. They each fund more or less in proportion to their GDP, and so it's a very international organisation. It's somewhere I worked for many years, I should say. A recent review in Nature drew attention to this centre and what's called the quiet revolution that's been undergoing in numerical weather prediction, particularly at this European Weather Centre. Now, an interesting, if I just go back to a few years earlier, there was an interesting letter in Science in 1927 by some people who you would think at first sight should have nothing whatsoever to do with meteorology. This was Marie Curie Henrik Lorentz and Albert Einstein. So Lorentz is the Lorentz of Lorentz transformations, if you know your relativity theory. And they, in 1927, actually were the first, as far as I'm aware, to advocate establishing an international bureau of meteorology. They recognized that meteorology was worldwide, the weather knows no boundaries, and doing something together internationally would be of benefit to everyone and would probably be able to do things that individual nation states were unable to do. So this is a remarkable letter which actually I only recently became aware of, and it's something I'm going to sort of come back to a little bit later. But in a sense, the European Centre for Medium-Range Weather Forecasts is a kind of manifestation of that. And I think one of these successes, the reason why it has been the leading centre and has consistently outperformed the United States National Weather Service, is that it really does draw on a range of scientists from different countries in Europe, and also the infrastructure, in particular computing infrastructure, has been, the cost of it is pooled by the member states, and therefore typically the European Centre has had supercomputing capabilities which have outclassed many of their rivals. So we'll come on to that a little bit later. However, I do want to just finish this last bit by pointing out that we're still not quite there. This was a very famous event not that long ago, just a month or two ago, Hurricane Patricia, which hit Mexico, and it was reckoned just as it was making landfall that it reached pretty much the deepest low pressure that has ever been recorded and the strongest winds ever recorded. It very rapidly decayed as it went inland. Now, this is a forecast for a few days ahead. It's based on an ensemble, which I'll talk about in a few minutes, and it makes a very accurate prediction of the track. So people were well warned of the position with some estimates of uncertainty. But what actually the graphs on the right show is the fact that the model systematically under-predicted the intensity. So this is wind speed with a kind of estimate of an error bar from these so-called ensembles. And you can see the actual wind speed and the actual low pressure lay outside the predicted ensemble, which is showing that the models are not actually picking up the intensity of these very severe weather events. And this is largely because of this resolution problem. They don't have the resolution to resolve things like the eye wall and the internal structure of the hurricanes well. We'll come back to that point later. So I just want to move through this, and I don't want to take up too much time on this first bit of the talk, but just moving on to seasonal timescales. You are aware that there's an El Nino going on at the moment. So an El Nino is a situation, so this is the tropical Pacific Ocean. These are the normal situation where the warm sea surface temperatures lie over the western Pacific. This is the ocean at depth. This is the so-called thermocline, which brings typically cold, nutrient-rich waters to the eastern Pacific. Over the warm waters, we have these intense thunderstorms, which in some sense drive a circulation pattern which maintains the sea temperatures, warm sea temperatures in the west. This is a kind of quasi-stable equilibrium, and every now and again the whole system kind of undergoes a transition where the sea temperatures, the warm sea temperatures start to slosh towards the east. That moves the thunderstorms with them. That in turn changes the wind patterns, and this whole thing sort of is like a bit of an instability. The whole thing kicks off and moves, all the warm waters move to the east. And this has a devastating effect on the fishermen because it shuts off this nutrient-rich water and therefore affects the fishing stocks. But more generally, it has an impact on weather patterns around the world. This is a prediction of the eastern Pacific sea temperatures from forecasts made sort of around at the beginning of May. And again, this is one of these ensembles. There are lots of individual now ocean atmosphere, coupled ocean atmosphere models, and they obviously predict some considerable uncertainty in what the sea temperature in the eastern Pacific anomalies will be, but there's clearly a movement towards warmer conditions. And in fact, the sort of mean, roughly the mean of this distribution is about where we are now. This is an actual trace of sea temperatures, and we're actually at a stage in the Eastern Pacific where the sea temperature anomalies have even exceeded the very big El Nino event of 1982-83. That's a pattern of what the sea temperatures are. So this shows very clearly there is some predictability in this El Nino on these multi-season timescales. And what I see very much a weather forecasting centre or a climate prediction centre in the 2020s doing is not just making predictions of sea temperatures or rainfall and things, but of some of the consequences of that. So I myself have worked on a number of types of applications of these seasonal predictions. One is towards malaria prediction. So we did work in Botswana showing how El Nino had a big impact on the likelihood of malaria epidemics through its impact on the local rainfall patterns. And I know an area that the Martin School is particularly interested in food security. Seasonal forecasts can have a big impact, and I think they will in coming years, in making estimates of crop yield around the world, places that are likely to be affected by drought and others that will have relatively good crop yield. And then finally, again, this is work by my colleague Peter Webster at Georgia Tech about the implications of all this for flooding, and in particular, he's done some very important work, I think, in countries like Bangladesh and Pakistan and others of seasonal forecasts of flood likelihood. And of course, this is becoming increasingly important because we do think, like the tropical cyclones, that also these extreme El Nino events may become more prevalent with climate change. Moving on to decadal prediction, I think one of the main applications in this area will actually be in advising governments and society more generally about what sort of infrastructure is needed to adapt to climate change. The government, I'm going to sort of, as an example of this, I'm going to focus on something rather parochial now, rather than talk about Bangladesh or whatever, rather parochial, which is the UK. And the UK has this Climate Change Act. So it's an act of parliament which commits the government, or commits the government to reducing carbon emissions on the one hand, but it also, as part of the act, it has a commitment for the government to produce what are called climate change risk assessments every 5 years. And the purpose of these is really to address what does government, what does business, and what does society more generally need to be thinking about to adapt to future climate. So let me just take one sort of small example, but it's something that sort of caught my attention this summer. We had a week or so, I suppose, where temperatures got sort of to continental levels. I don't know whether the continental people would call it a heat wave, but we had temperatures well in excess of 30 degrees. And you probably noticed that all the trains suddenly had to run slowly. And, people from other countries kind of laugh at us that our train network is completely crippled by what are sort of not, by their standards, maybe not necessarily all that high temperatures. So what's the difference between the UK and other countries? So this was something I picked out from whatever it is, Railtrack or something, web page, where they actually talk about this problem of buckled rails. And they note that some countries use slab track, where track is laid on reinforced concrete slabs rather than on sleeper and ballast, preventing tracks from buckling. The installation cost of slab track typically costs 4 times as much as track laid on sleepers and ballast. Even taking into account the savings in maintenance and disruption costs, it is hard to make a business case, they say, for slab track. Well, okay, that may well be the case, but I think one of the kind of key areas of work that I see a future climate prediction agency getting involved with in detail is with people who are expert in these things, is trying to assess when the business case will be made for this type of investment. So that will require knowing how much more likely in the next decade, the decade after that, or the decade after that, these plus 30-degree temperatures will occur. And it will require an estimate of the disruption to the economy and to the lives of people and so on from the rail network being sort of basically shut down during these periods. And that will inform on when the business case can be made for this type of investment. So I see this as a very kind of key area for future climate prediction work. So I'm going to move on now to 100 to 1,000 years and perhaps 100 years. And of course, the big issue there is what is climate change going to be like globally. Now, I don't know if people went to Martin Rees's talk at the Sheldonian a week or so ago, but he noted the point that, that climate predictions about global warming are uncertain because largely of the interaction of increasing CO2 with the water cycle. And perhaps the biggest of these is what clouds, how the cloud cover is going to, if you like, react to increasing levels of carbon dioxide. And we are actually quite uncertain about this. And even to the extent that we're not really certain whether clouds will amplify the effects of CO2, so make it warmer than it otherwise would be purely from the radiative greenhouse effect of CO2, or whether it will damp CO2. Now, most of the climate models suggest it's going to amplify, so it's bad news, if you like, for climate. But on the other hand, I think we have to be extremely cautious about that result because the models don't resolve clouds. They're represented by these simple formulae. And I want to just give you an illustration of how it could go the other direction. So this is a picture of an extratropical low-pressure system seen from a satellite. And you've got basically very cold air coming over a relatively warm ocean. And what happens is these essentially thunderstorm-like clouds, cumulus clouds, bubble up as a response to a kind of convective instability. But these clouds are actually organized into the shape of sort of a little bit like hexagonal cells, which is a characteristic of what's called Rayleigh-Bénard convection. You can see it in the laboratory very simply. You get this organized type of convective cloud, convective motion, where actually the clouds are largely on the boundaries between the cells, and most of the cells themselves are clear sky, are sinking air. Now, if the effect of increased carbon dioxide is to create this type of organization to convective clouds, particularly in the tropics, what it will do is actually open up large areas of clear sky from which heat can escape to space. And it may, therefore, this could actually act as a negative feedback and something that would be, in a way, welcome. This is sometimes called the iris effect. It was proposed by climate scientist Dick Lindzen from MIT some years ago. And I think this is an important paper from the Max Planck Institute earlier this year, showing that our inability to model this organizational structure means that we cannot discount the possibility that with this iris effect, the sensitivity of the climate to CO2 might actually be a lot lower than it is characteristically in IPCC models. I think this has political consequences because in Paris at the moment, we're concerned, for example, that India is not making big commitments to cutting its coal consumption. But actually, if climate sensitivity is less than we think, I think there is breathing space for countries like India to come up to speed. And we shouldn't necessarily treat them as sometimes is done in a critical way. So I'm just making the point that it really is crucially important to understand better the nature of how the hydrological cycle interacts with increasing CO2. It could go in the sense of positive feedbacks, which is going to be really bad for humanity, but there are possible mechanisms where it may go in the other direction. And I really can't see any, we've got to just basically model this and understand this. We can't do it at the moment because we don't have the computing capacity. So that's something I want to come to. Geoengineering is an important sort of plan B that, again, the Oxford Martin School has done much work on, spraying sulfate aerosols in the stratosphere, for example, to offset increasing CO2. I think the point I would just make here in passing is that we don't yet understand the regional impacts of these types of geoengineering fixes. We don't understand what it'll do to the monsoon systems, to El Nino, to all the things really, and indeed to things like the moisture supply to the rainforests. So again, in the 2020s, we've really got to tackle this problem seriously, trying to understand better the effects on regional climate. And just because, again, it's work that's being done in Oxford, I just want to make the point that another application of climate models is in trying to attribute actual events to things like climate change. So when we see some extreme event, whether it's a hurricane or a heat wave or a drought or something, can we say, you know, the likelihood of this occurring has increased by some fraction as a result of human climate change? So there are groups now, Climate Central in the US, that link with the Environment Change Institute here in Oxford that are trying to do this in real time. The National Academy of Sciences, on the other hand, has recognized that we need to be a little bit careful about our capability in this area because simulating extreme events is often something that the models don't do that well. So this is, again, an important area for research and is something that will certainly be an important aspect of climate prediction in the next decade. All right, so what do we need to predict the future? Well, I think basically three things. We need very good observations, as I say, for initial conditions and for verifying the forecasts. We definitely need big computers, and I'll talk about that, and we need very good people. Now, in Europe, we have, just want to very briefly pass over observations, because we have an example, again, another example of where we pooled our capability, essentially the aerospace industries in Europe have pooled their capabilities, and we have a European space agency that does some fantastic work. You probably saw today it's launched a mission which will sort of start a space-based capability for detecting gravitational waves from distant supernovae and galactic collisions and such like. And you know, you're all aware previously of the famous mission which landed on the comet. There's also a branch called EUMETSAT, so European Meteorological Satellite Agency, which is in some sense a part of ESA, which is more focused on satellite instruments that look back to Earth. And this provides a lot of crucial data for initializing forecasts and for actually determining what goes on in the world at any time. You know, you might want to just reflect on the fact that back in the days before satellites, there were often hurricanes that occurred which just were never seen because they never made landfall. So it's very hard to know when you go back before the satellite era whether the statistics about hurricanes are really genuine statistics or just reflecting the fact that we didn't see that many that time ago. So observations, actually, in my view, we're doing very well in terms of our European collaborative effort. But supercomputing, I think we do less well. So I'm just going to spend a few minutes just talking about that. So I've tried to convince you that, if you like, increasing the number of Russian dolls is important, both for the atmosphere and the oceans, getting better estimates of these intensities of cyclones, getting to the stage where we can start to resolve cloud systems, and there are many aspects in the oceans that need high resolution as well. But supercomputing is not only needed for increasing the resolution of models. We need to, models over the years have become more complex and need to become more complex. So here's a slide showing what a climate model was like in the 1970s. Basically, it was just an atmosphere and the ocean was a boundary condition, and the land surface was a boundary condition. Then people developed land surface models and then ocean and sea ice models. Then we started to put in aerosols And then we started to put in some biogeochemistry, carbon cycles, and then other types of chemistry. So becoming more and more and more sort of incredibly complicated, and that's another sort of axis in the one of the driving mechanisms for supercomputing. And then the third axis would be ensemble. So as I said, these days we never make a single prediction into the future. We always make a range of, an ensemble of predictions where you typically might vary the initial conditions in the sense of the reflecting the uncertainty, always a slight uncertainty in initial conditions. And you might also introduce some uncertainty in those equations in the rusty tin can, if you like. You vary that a bit, reflecting that's not a perfect, it's not even that good a measure of what's going on at the subgrid scale. And you get some occasions where the ensemble spread is relatively modest, and other occasions where the ensemble spread is enormous, telling you this is a very unpredictable situation and you can't trust any specific forecast. You have to think much more probabilistically about what's going to happen. But when the ensemble sticks together, then you can be a little bit more certain. So ensembles are another important, crucial aspect of a climate prediction service in the 2020s, being able to forecast not only the meteorological variables, but the uncertainty in those variables. So my own view, and this is something I've published a couple of papers on in the last few years, is that we in Europe need to be getting together like we do for the European Space Agency, and maybe like as we do in high energy physics, and pooling resources for developing really cutting edge computing for climate prediction. And that was another commentary in Nature that, if we need to build high resolution models which can resolve these types of things, it's going to be likely beyond the budgets, particularly these days with the big cuts in DEFRA and DEC and BIS and things, the departments that fund climate modelling. If they're going through cuts, then the only way we can improve our capability is to pool resources in Europe. But we have a slight problem in this area. Well, I say slight, it's actually probably a big problem, which is that when you look for supercomputing, there's actually not much going on in Europe. I say that actually, the French have a company called Bull, which is trying to get into the first tier of supercomputing, but I think at the moment the leaders in the field are outside Europe. So many weather and climate centres, such as the European Weather Centre and the Met Office in Exeter, use Cray computers. IBM, NVIDIA are also coming on. Well, IBM has been a long leader in supercomputing. But these are American companies, and that's one of the problems. When we talk about investing in supercomputing in Europe, we don't have quite that level of industrial return that we do when we invest in aerospace. The Americans, on the other hand, this is where they do have a lead, and in fact, just a couple of months ago, Barack Obama signed an executive order to actually develop a national strategic computing initiative in the US. And really what this is about is putting resources into building the world's first exascale or exaflop computer. So exa means 10 to the power 18. So 10 to the power 18 floating point operations per second. That's an exascale computer. We're currently at petaflops, so 10 to the 15, 10, maybe 10 petaflops. And the goal of this initiative is to build the first exaflop. And this is really, exaflop computing is what's needed to get down to these high-resolved, cloud-resolved climate models. Interestingly, though, it's not entirely clear when the first exaflop computers will appear, and this is something I picked up on the web. Supercomputing director bets $2,000, doesn't sound like a great deal of money, that actually, anyway, that we won't have exascale computing by 2020. And the reason is that supercomputing is running into a big problem at the moment, and it's to do with energy. So it's actually worth just reading this out from this website. This guy, director of a supercomputing lab, is saying that that's precisely where exascale level problems stab out stab our concept of efficiency in the back. 1 exaflop is 10 quintillion flops per second. When you're working with 18 zeros, picojoules start adding up. It's theoretically possible to hit exascale computing with current levels of technology if you can afford to dedicate 100 megawatts of power to the task. But the challenge is to bring exascale into the 20 to 30 megawatt range. So this is actually the crucial sort of constraint on our ability to develop yet faster computers. It's energy demand, power consumption. Now that in turn is driving certainly a lot of work in my own group in trying to address this problem from, let's say, a more theoretical point of view. As I mentioned, we're trying to solve equations like this. It's a nonlinear partial differential equation. We can't solve it exactly. This is a continuum equation, so it's an infinite, what a mathematician would call an infinite dimensional partial differential equation. And we solve it by projecting it onto some finite grid representation or some set of wave-like motions, for example. And that means that at the truncation scale, the motions near the truncation scale are severely compromised. They're inevitably compromised by this finite truncation. So there's an important question here which kind of sits at the interface between mathematics of these equations and computer science, which is what is the actual real information content in the variables as a function of scale? And are we traditionally representing particularly the small scale variable with more bits than is justified theoretically? So traditionally, all variables in a weather or climate model, as indeed most computational models, are represented with what are called double precision, 64-bit numbers. And the question is, how many bits really do we need as a function of scale? So there are these things called IEEE standards in computer science, where you represent numbers with either 64 bits, these are all double precision, or 32 bits, single precision, or even 16 bits, half precision. And the energy is basically determined by how much data is moved around on a computer. That's the thing which determines the power consumption. So the fewer bits we can move around, the less energy will be taken, and then potentially the faster the computer can go for a given amount of energy. So trying to represent the millions of variables with just the right number of bits is a crucially important question. There's also the issue about determinism. Computers have traditionally been deterministic. If you do the same calculation tomorrow, you get exactly the same answer as today. But again, that puts an energy overhead on the computer. You have to ensure all the transistors are immune from noise, the noise of the electrons going through the transistors. And reducing the voltage across the transistors can have quite a dramatic effect in power consumption, but with very, very little introduction of error. And so if you can tolerate a certain amount of error or imprecision, again, this is another route to reducing energy consumption. This was a chip produced by a colleague of mine from Rice University in Texas, which originally was designed for an iPhone. It's basically showing that image processing in a low voltage, imprecise chip is hardly degraded compared with a precise energy intensive chip. And that could prolong your iPhone battery maybe for another day or so. But I think a much more important application is actually in supercomputing. So just to put it schematically, the idea is this. You have a choice between solving these Navier-Stokes equations very, very precisely with 64 bits. You know, everything is perfectly accurate. All these Russian dolls are beautifully accurate. But you have this terrible truncation scale which is hurting you, and you're representing a load of stuff very imprecisely below the truncation scale. And the question is, what is preferable, this or a situation where you start to degrade the Russian dolls? They're still Russian dolls, but they're degraded Russian dolls, and they're more and more degraded as you get to smaller and smaller scales. And the question is, would this give you more accurate forecasts than this? And our belief, and we got some very evidence for this, but I'm not going to dwell upon it here, is that we will. So my hope is that as we go into the 2020s and we go into this exascale range, that computer vendors will start to recognize the importance of imprecise computing and imprecise calculations. And this will be of enormous importance for weather and climate prediction, and I think it will for a range of other computational problems in science. So just in 2 minutes, I want to finish with the last point, human resources. I haven't talked about that. And this was an impassioned plea from some colleagues of mine, which got reported in Nature, saying that we need to somehow convince physics graduates, when they've done their degree and they're looking for PhDs to do, to come to us in computer science, in climate science. We need to somehow engage with these very quantitative, this could be mathematicians as well, I suppose. But the article finished in a rather sort of negative way, in a sense, because it quoted a fluid mechanicist who also is involved in climate work, Paul Linden from the University of Cambridge. And he says, we offer courses in climate science and our students do recognize the importance of the field, says Paul Linden, Fluid Dynamics Research at the University of Cambridge. However, most physics students would rather study with Stephen Hawking, who's a member of our faculty. So he's saying, for all the sort of importance of climate and so on, the top students are often attracted to do PhDs in cosmology or, the Higgs boson, or in mathematics study Fermat's last theorem or something like that. So my view about this is that we're wrong to try to necessarily attract large numbers of people just at the graduate level. But where I have found, in my own experience here in Oxford over the last few years, is that there's quite a large body of people who, having done their PhDs, whether it's in number theory or high energy physics or cosmology or whatever, and maybe even done a couple of years of postdoc, they start to get a bit of a social conscience and they think, well, actually, I should be applying all this stuff to something a bit more useful in the world. And I think this is the time when we should be attracting these people, and I think there's a potentially enormous resource here. But it's actually, but it's sort of tricky, if, for example, if I'm recruiting a postdoc and I've got a choice between people that have a lot of experience in the field and people that come in with essentially no experience, it's quite difficult for me, much as I would like to necessarily hire them. So my own view is that there is a great need for the research councils to step in here and offer kind of retraining programs for people like this who want, at a sort of later stage in their careers, to make that jump to climate science, and I think we could benefit enormously from them. So, okay, so I've just about finished now. I hope I've convinced you that reliable climate prediction is of importance, and I think will be of increasing importance for society, particularly as we start to see more and more extremes as climate change kicks in. And, where we are now is fantastic, but there's a long way to go to improve reliability and to develop our capability. I think supercomputing is going to be a real important big bottleneck, and I personally believe, I very much follow Einstein et al. In saying that we need to do things internationally, pooling resources internationally, and maybe developing this notion of inexact computing are going to be important considerations for the future. And just finally, I think the research councils could do more to help retrain post-PhD physicists and mathematicians into these areas of environmental science. Thank you.
Thank you very much, Tim. Okay, we've got some time now for questions. We have a roving mic, so do wait for the microphone to get to you. And there's a question at the back, the mic will come to the front.
Oh, great. Thank you. First of all, many thanks for the talk. It was very interesting. And my question is, so when you're using these large scale or climate models to actually predict what's going to happen in a future at finer scales, how do you see that the error replicates like throughout those models? Do you think that it's or how much do we know about these uncertainties?
I didn't fully understand you. Can you just say it again? Sorry.
Yeah, so my question is, so when you're using large-scale models to actually understand what would happen in a future at finer scales, so when you're actually like jumping from large-scale models to finer resolution models,
Yes.
how do you see that the error propagates throughout those models?
How does the error propagate?
Yeah, yeah. Do you see that as a major source of uncertainty if we want to understand, I don't know, like weather forecasting or seasonal forecasting in the next 5 or 10 years?
Well, I mean, as you know, I mean, by increasing resolution, what you're basically doing is solving those equations more faithfully. You're solving those equations more accurately, and I mean, there's a you know, as I say, the real kind of holy grail in the next few years is to be able to resolve individual thunderstorm clouds and to move away from these very simple so-called parametrization formulae for thunderstorm clouds. You know, and an example of where that can lead to a more accurate prediction is, as I say, in the ability to simulate this type of organization of cloud systems, which will determine, you know, the rate at which heat is lost to space. I mean, if you're thinking about, you know, upscale energy transfers and things like that, I mean, it is true that in terms of weather prediction, the upscale transfer of energy can ultimately limit it determines in some sense the predictability horizon of an initial value problem. But upscale energy transfer is not completely ubiquitous. It's something, it happens sporadically, intermittently, and at sort of particular parts of the world. So you need the high resolution models, but you also need these ensembles to determine ahead of time where the predictability is going to be lost, but more importantly, where predictability is going to extend out for relatively long periods of time. So as I say, it's not high resolution by itself would be no good. You need it with an ensemble capability in order to investigate how these upscale errors grow.
Given the uncertainty of climate models, how do you think that interdisciplinary work around climate change can most productively proceed?
Well, you know, I'm very, as I say, I'm trying to, I gave you a few examples, but what I think we need to do much more of is couple these models to the impact models, whether it's agriculture or health or, you know, hydrology, whatever it is, couple these models to the impact models. And what you then do is whereas previous, you know, just with the climate models, you have probability distributions of rainfall or temperature, which kind of reflect the uncertainty. That then goes to a probability distribution of of flooding in a particular instance, or a probability distribution for malaria epidemic, or a probability distribution for, for crop yield or something like that. Now, once you get to that level, then I think you have then the user community then has the capability of making rational decisions. If you can make decisions once you have a quantified estimate of uncertainty in the variable that is relevant to your decision process. I suppose that's the point. So, the fact, what I'm certainly not saying is that the fact that there clearly is quite a significant and substantial probability of cloud feedbacks being positive means that there is a very substantial probability of going towards very dangerous levels of climate change in terms of all of the kind of variables that affect society and the biosphere. Where a scientist like me can't perhaps make the judgment is whether that whether that probability is big enough to take various decisions that might need to be made. But what I think the climate science should be doing is interfacing much more quantitatively with these impact models, so these probability distributions can be made much more quantitatively, and I think that will ultimately be for the benefit of decision making in a range of areas in society.
It's coming forward.
Hi, I was going to ask sort of quite a follow-on question to that. How much of a step change is that going to be for climate science to try and couple to those impacts and consequences? You talked about probability distributions. Do you need more data gathering? Is that the kind of thing these satellites can do, or is it very, very different?
No, I don't. I mean, I just see it as I just see it as an interdisciplinary problem, and I don't think actually there are too many barriers of that nature, other than it needs people to work together, and again, it needs research councils, maybe different research councils, to recognise that this is a useful area to fund, across disciplines. I mentioned a couple of areas where I've done some work more on the seasonal timescale, working with people on malaria prediction. So again, there you need primarily, it's based on rainfall data, temperature to some extent. And we came out with probability distributions of malaria epidemic in Botswana. We used Botswana because there was enough epidemiological data to know whether our predictions were any good or not. We could test them on hindcast. And then that can determine things like whether you send out, whether you target bed nets and things for that particular region ahead of time. But this just requires, people in climate science, I'm in physics, to work with, people in zoology and different disciplines, similarly with crops and so on. So I think it's, it can be done. I don't think it doesn't need much more data or anything. But we're talking about, that's the only other problem. We're talking about big data here. We're talking about, these models we're talking about big data sets, and this is not a trivial issue, but it's one that can be done if there's a will to do it.
Another somewhat related question, sorry, but so we use the future flows data to predict the impacts of, say, for instance, climate change on water supply, and we see that that's based on that's downscaling of only one of the ensemble of models, and the ensembles give very different results. Does that ensemble, or even one of those models, incorporate some of those uncertainties, such as the iris effect that you spoke of? And if not, why not? Couldn't they show the bounds of that uncertainty in their ensembles?
Well, I mean, the situation at the moment is a little bit unsatisfactory. I would say that we have different institutes around the world that develop their own models, and in particular, they develop these subgrid parameterizations individually, there is a kind of assumption that if we pool all those models together, we get a credible estimate of uncertainty. But my own personal belief is that is a sort of a bit of too much of a blunderbuss approach to the problem. That in some aspects, these multi-model ensembles are grossly overestimating uncertainty, and probably in some areas, like the inability to represent the iris effect, they may be underestimating uncertainty. So again, this is another reason for me that we need to, the community needs to work together we need to move away from these kind of nationally based centres to a much more international pooled capability. And then I think we'll get much more credible estimates of uncertainty.
I'm interested in whether you use or is there any mileage in using steady state models, given that you've mentioned the different complexity and computational power required. If you move to very long time scales, so ignoring seasonal variation, etc., and just sort of forgot about the time differentials in all your equations, they'd be much simpler to solve with much less computing power required. So I'm kind of wondering if you could just sort of find out what the overall carbon distribution would be, sort of given carbon released from fossil fuel sources, how much would be in the deep oceans and other places, and sort of solve that relatively mathematically simpler problem first, and then say, well, what climate would that give?
Unfortunately, it's not as simple as that, because the time variability of all the all the processes that go on in the climate system actually contributes towards determining what the time averaged. So you can't. It's not a linear problem. You can't just say, okay, here's a time mean, and then I got some fluctuations about the time mean. I'm not interested in the fluctuations, so I'll kind of forget about them and just think about the time mean. But actually, the fluctuations are contributing non-linearly to the value of the time mean. So you can't model that so-called steady state without assuming in some ad hoc way what the effect of the variability is on the time mean. So it's not a well posed problem at a sort of at a mathematical level. You can obviously make an assumption about that. You can model, with a simplified model, a kind of steady state climate, but you're making implicitly assumptions about what the time variability, how it contributes to that time mean, and those are just ad hoc, and you don't know. The problem is you don't know as you change, for example, CO2, you don't know from that type of model whether the effect of the variability on the time mean is also going to change with the CO2, because you don't have that represented in the model. There is no shortcut to a kind of rigorous approach to this other than to try to solve those equations accurately. I mean, I'm not, that's not to say there isn't value in looking at simpler models and more idealized models, because they do give you ideas about the importance of different mechanisms. But as a tool for informing policy at the quantitative level, I don't see an alternative than to do one's best in solving those basic equations.
Yes, I was wondering what you thought about the form and the level of public engagement in climate weather, whether it's helpful that there's a lot of wild speculation every time there's a dry summer or
Yes.
Some flooding or
That's right.
whatever, and even in Parliament they're talking about, they show this about long-term climate change. And then you have the Daily Express, you happen to show that, but they're every other day they have some wacky
Yes.
prediction or forecast.
Right.
But maybe it shows the level of, that there is a great deal of interest, even if it's strangely characterized. And you see some response to that, it seems to me, in, for example, naming storms, which doesn't seem to me to be a good reason for other than Americans do it, so we should do it as well.
Right.
I would think that's all part of it.
Yeah. No, I think on the whole, actually, the UK public is fairly sort of sensible. I think takes a very sensible view about weather and climate. I think one thing that's been helpful, and I think one could go further along this line, is in recent years on the weather forecasts, the forecasters have been much more open to being uncertain when they aren't sure what's going to happen. Whereas in the past, I think there was a feeling that somehow they were, they were unprofessional, if you like, if they, unless they knew exactly what was going to happen in the next 3 or 4 days. And I think that does help the whole sort of debate about the fact that our policy on climate mitigation doesn't require us to be 100% certain about what's going to happen. It's just that it's enough that there's a significant risk of, potentially catastrophic effects to climate. And I think I got a feeling that most people in the UK understand that. In the US, unfortunately, it is much more polarized and, and very politicized as well. Yeah, I mean, I don't know. I hope most people take the Daily Express headlines with a pinch of salt. I mean, it is true that the Met Office. Well, I don't know. We can discuss the Met Office barbecue summer. I mean, people take that as an example of a disastrously bad forecast. People lost, I think, a lot of trust in some of these forecasts as a result. I mean, to be fair to the Met Office, the actual phrase was odds on for a barbecue summer, so they did somewhat express it probabilistically, which is good. Perhaps they could have been a little bit less kind of glitzy in the way they did it. But I think it's clearly important in science that you don't over-egg things and you don't tell things with more certainty than is justified. But on the other hand, I like to feel, I do sometimes worry that the government feels that they know everything they need to know about climate and they don't need to fund any more of the science. But, if we want to reduce these uncertainties, and I think things like the Iris effect is a crucially important one, we do need to keep funding basic science. But it doesn't have to be that expensive, actually. And as I say, if we pulled our capabilities, for example, in Europe in climate, it need not cost the taxpayer too much more. So, yeah.
Hi, following on that note, given the gap that still exists, a sizable gap between what climate scientists are saying we need to do and the changes that policymakers are willing to implement, do you think that our ability to predict and on more computational scale to be able to predict climate change in the future will lead to a shrinking of that gap and make more informed adaptation and mitigation policies?
Absolutely, I do, yes. And as I say, I see the gap closing, because there will be a much more quantitative linkage to the impact modelling, and it's the impact modelling that then will directly affect the government, government policy. So I see, through a series of steps, governments being much better informed about future investment needs, for example, on adaptation. I mean, at the moment, for example, we haven't really got much of a clue about multi-year drought. Do we need to invest? I know we have a lot of concerns about flooding and so on, but the converse is that there may be more frequent occasions where actually drought occurs on multi-year timescales, and for that we need more reservoir capacity. But at the moment it's very hard to get anything very much quantitative out of this from the model. So that's just another example of where a much more interdisciplinary, I suppose, approach will help to get the link between policy and science closer.
I think I know the answer to this question before I ask it. But is it possible to run meaningful climate models nowadays outside of a supercomputing environment?
Well, that's a very good question. Because there's a fantastic project which has been pioneered by a colleague of mine, Miles Allen, here in Oxford, which has got the sort of exploited the power of PCs around the world. And what they've done is to package a version of the Met Office's climate model, but that was kind of operational, I don't know, 10, 15 years ago or so. So it's what by today's standards would be called a low resolution climate model. But the advantage is you can do enormously large ensembles. You get tens of thousands of members, because tens of thousands of people around the world are picking up the code and doing integrations. And I think I'm absolutely convinced that useful science can be done with these systems. But in a way, it's not so it gives you indications about issues that might be of concern, but at the end of the day, there isn't a substitute to going to high resolution. So I think, yes, useful science can be done outside the supercomputer, but it's not going to be a complete substitute.
This is not a very technical question. What are you most excited about, and what are you most worried about?
Is that in general or just in climate?
I thought you might ask that.
Well, you know, I mean, I don't know. I get a buzz. I get excited about problems which have both a societal sort of impact, but can be, on the other hand, you know, is amenable to sort of, you know, basic mathematics and physics. You can kind of where you know, where I can go and I mean, I wrote a paper not that long ago with a mathematician in the Maths Institute, where we just analysed the really sort of abstract mathematical properties. I won't bore you with the sort of technical details here, but really sort of quite difficult mathematical properties of these Navier-Stokes equations from almost a kind of pure mathematical point of view. And that does excite me, actually, the fact that you can do a problem at a kind of one level which seems enormously abstruse and hardly sort of relevant to anything, but on the other hand has this fantastic kind of downstream application. And I think, you know, this is where perhaps the Oxford Martin School is so wonderful, that it brings together these people from different areas, from very pure science, if you like, and very applied science. So that gets me kind of excited, I think. Anything that sort of has that range. What gets me depressed? Well, unfortunately, the politics, you know, the politics of climate change gets me depressed. I mean, certainly the pathetic things that go on in some of the US Senates and Congresses, I think, is enormously worrying, that people in power have such sort of very simplistic views about the world. And I don't know how to change that exactly. But, you know, maybe one day.
Prospect of Brexit, I suppose.
Sorry?
I suppose also the prospect of Brexit would be depressing, given that
Yes.
there's so much collaboration can be done at European.
Yes, absolutely. I don't think people realise how important the EU is for British science. And it's not just my field. It's right across the piece. Yeah.
Well, I have questions regarding the climate physics and the model side. So you have mentioned that there's approximation, for the sub-grid, for every single grid,
Yeah.
Across different institutes that
Yeah.
develop those
Yeah.
models. So my question will be, like, for those approximations, like, does the applied models actually have opportunities to sit down together and go through those approximations, and then look at whether those approximations are actually made in the higher latitude or in the tropics, like the parameterizations, to sort that out so that you can reduce the uncertainty and perhaps be useful for projection purposes.
You're saying comparing the different models is useful?
Yes, so you can look at the approximation, parameterization for every single model.
I mean, a lot of models. The problem is there are systematic errors which are actually common across all of the models. The tropics, so, you know, the what are called the tropical interconvergence zones, getting those positioned correctly is actually a problem common to all. To pretty much all models, and it sort of indicates that it may not be so much the details of the parameterization that's the problem, but just the very fact you are parameterizing it, which means you're making all the cloud systems slave to the larger scale flow. That's the problem. So you can go so far, and people do. I mean, there's lots of these so-called model intercomparison projects. But it's not a panacea for getting to a stage where You know, what I would like to do, I mean, what I, you know, sort of aspire to is being able to produce a model where if I give you the output of that model or a sort of trained meteorologist, they actually couldn't tell whether they're looking at a model or the real world. And we're pretty much there in weather forecasting. If I gave you a kind of a simulated cloud field from a weather forecast model 2 or 3 days out, you probably couldn't tell whether that was from a satellite looking at the Earth, the real Earth, or whether it was looking at this simulated weather from a model. But if I go out for a year or 10 years or something, there are these characteristic biases that start to develop, and any trained meteorologist could tell immediately whether they were looking at a model or the real world. And we haven't got to the stage where it's kind of like a Turing test, you know, for models. Can we get to the stage where we just can't tell whether we're looking at a model or a real world, like looking at an artificial intelligence or a real human? And we haven't got to that stage yet, and that's where we need to be.
Okay, I think we've had all our questions. So thank you all very much for coming, and one more thanks for Tim. Thank you.